Hello again, folks. Today we're going to be going over, as promised, the solutions for what would have been test number 2. This consists of chapter 7 and chapter 8 material. All right. What you'll have available to you is technically this packet. All right. Here's test number 2, blank anyhow. This will be available in Canvas announcements, along with the link to the this video. All right. You can see it's several pages. All right. It's not multiple choice, which I would have preferred, but we're going to go through each one of these. And it's a good summary of basically what you need to know up to this point, insofar as those 2 chapters are concerned, okay? So if you would, maybe take this out, print this, and we'll go over the answers now. Okay. Hoarse, sore throat I have. Seems like always. Okay, let me get rid of this. You got erased nicely for once. Okay. It's a bit dark, so maybe I will adjust this. Is that a bit better? Move this so slightly. Yeah, that looks better. Okay. Alright, now I tried to give you sort of hints so you didn't have to go digging for information. In the case of these first 2 questions, I put a number line. If you do enough of these type of problems that are the metric system conversion, you don't really need to have any sort of visual aid, but they're there in case you need it for right now. All right, so for problem 1, I just wanted you to convert, what is it, 9.55 milliliters to so many liters. All right, now here's the easiest thing to do. Draw a number line with 7 increments, 3 here, and 1 in the middle. The middle one is the actual base unit, which traditionally at least used to be a capital L. Your textbook uses a script lowercase l, I don't know why. I'm not trying to be defiant, but you should at least fill in this diagram with the units that are between, okay? Or at least have know where the start and where the end is. The one nice thing about doing it this way is that it also tells you which direction you're moving your decimal point when you're converting from the smaller increment to the larger increment. So let us say you start here, all right, and you're going here. How many spaces is that? 1, 2, 3. 3 in that direction. So you take this decimal point and you make 3 waves instead of 3 leaps, right? 1, 2, 3. And then fill in the void. Right? This is the correct answer. It's the same amount, it's just expressed using a larger increment, a larger unit. If you want to be fancy, a lot of times what they'll do is they'll put an extra 0 up in the front. This is supposedly to make it a little bit easier to see where the decimal point is. I think that's debatable, but anyhow, it is 1, 2 zeros in front of the 9. Okay. The next one is similar. All right. Convert. Let's see, 117 kilograms to so many. DG would be decigrams. DA would be deca. They're on opposite sides of the ladder here. All right. So again, make 7 increments, 3 here, and 1 in the middle. And then at least fill in the units that would be relevant. Let's see. Kilograms is on the far end, gram is the actual base unit. All right. In between there is hectagrams, decagrams, which is DAG, D-A-G. And I hope that's visible from far away. And deci is here. It would be centi and milli if you wanted to continue. Anyhow, this is where you're starting, this is where you're going. If I were a little bit wiser, I would have maybe made this a little bit spaced better. So I'm going to fix that. Okay, there you go. 1, 2, 3, 4 spaces, and you headed in this direction. Oh wait, I'm doing it backwards. Forgive me. Shame, shame. Starting here, going there. All right. Reading my camera. All right. So starting here, 1, 2, 3, 4. Go 4 spaces that way. Now, when you have a whole number like 117, just realize that the decimal point would start there. Right, so you often would have to put the point yourself, it's not given to you. All right, and then do the same thing as before, make that many waves. Right, so 1, 2, 3, 4, and then fill in the voids here, the pockets, if you will, with zeros. 1, 2, 3, 4. Now, stylistically, at least in the United States, every 3 we put a comma on this side, the left side of the decimal point, not ironically perhaps on the right side. So it would be 1,170,000 decigrams is the equivalent. It looks different, right, naturally, but it is actually the same quantity. It's just using a much smaller increment, right, much smaller unit. So it is arguably more impressive, right, because it's such a large number, right? Nonetheless, it is still 117 kilograms, right? Which is, maybe approximately the weight of a person. Now, maybe a tall, large person. I forget offhand, I think the conversion factor, 1 pound is 0.04 kilograms, or if you look at it from the perspective of kilograms, 1 kilogram is 2.2 pounds. So you can convert that, and there's a problem that's coming up like that. No one gets measured in decigrams, do they? They could, we just don't do that. The next one is how many times larger is a square kilometer than a hectare. And a hectare is just an alternative for a square hectometer. So this is essentially asking you in a more verbal way. Let me point at it on the camera here. This is number 3. How many times larger is a square kilometer than a hectare, which is again a square hectometer? This is a much more verbal way of basically saying things like this or this. So you could translate it, especially if it makes you feel more comfortable. Let me start with a picture here. If you have a square kilometer, I'm just going to abbreviate it SQKM. That is an area, right? Literally an area. And it's a square, so it means that the dimensions this way and this way are a kilometer each. Right? But, and perhaps the visual aid would be better in this respect. Here's a diagram I had drawn you a while ago. A meter is the base unit for measuring lengths. And if you go to increasingly larger units above this, the next one would be deca, which you would attach to the base unit, and then hecto, and then kilo is just above it. If you are a distance of 1 space apart, you are 10 times larger than the base unit here. The same could be said for the space between hecto and deca. A hectometer is made of 10 decameters. That is a rare thing that almost never happens, but you could think about it that way. And similarly, kilometers, there would be 10 hectometers in 1 kilometer. What I'm getting at is that it's 10 of these to make this, it's 10 of these to make this, it's 10 of these to make this. Alright. Normally we just go from here to here, which is why this is 1,000, because it amplifies by multiplying. But knowing that would help answer this question, because if it's a square kilometer, and we're considering hectometers instead, this would be 10 hectometers. And this would also be 10 hectometers, HM. So if you wanted to build sort of a conversion factor, instead of it being 1 kilometer times 1 kilometer equals 1 kilometer squared, 1 squared kilometer, we could have the equivalent of 10 hectometers times 10 hectometers is equal to 100 hectometers squared. That is still not answering the question, but it's helping us. Because what is it doing? It's making a conversion factor. It's to say that if this is the relationship individual sides, then this is the relationship as an outcome. Which again, if you wanted to make as a conversion factor, you could write in the style of a fraction, either like this: 1 square kilometer is equal to 100 hectometers, or if it's more convenient, write it upside down, like so. Alright. Anyhow, what is the relationship to answer the question? The question is, how many times larger is one than the other? What's the ratio? 1 to 100. So it is 100 times larger. And that is the answer. The reason that I seem to be perhaps belaboring the point is that when you get to the next question, you have to be a little bit more careful. It's less verbal, all right? And it is misleading for that reason, actually, because when you get to the next problem, you may jump the gun. Is 4. Yeah, I'm choking first thing in the morning. Okay.
I wonder if there is something in this hallway that is trying to kill me.
Jeez, I hope not. I'll pass out. You know, there's no one can help. Alright, enough of that nonsense. Here's 4. 4 is a little bit more stylistically similar to problem 1 and 2. 10 cubic meters is how many cubic centimeters? We do actually have established a unit conversion. And you could dig for that if you want to, but you could always reason it through, and I want to encourage that. Here's a cube. Start by drawing a picture. 1 square offset behind another. Connect the vertices. And you have a cube. Chitty, isn't it? Okay. Now, anyhow, the dimensions are a length, perhaps in the front. That would be 1 meter. A dimension down the side here, which would be 1 meter. And a dimension for depth or height, whichever you prefer, which would also be 1 meter, if in fact this is a cubic meter. I'm spelling it the American way, which would be ER. Not that it's better. It's more defiant than anything. Alright, anyhow. A volume, which is what something that is cubic would signify, is these three things multiplied. So a meter times a meter times a meter, which is not going to change the digit, it's still 1. But the abbreviation for the unit would be meter, meter, meter would be meter cubed. Okay. Now that is what it would be made of. Think about the individual sides, their unit in respect of meters to centimeters, regular centimeters. A centimeter is 100 centimeters is 1 meter. So we put 100 here, here, and here. Yep. Okay, so if it was 1 times 1 times 1, you would replace that with 100 times 100 times 100, which is in theory this. Shortcut that works for powers of 10 at least. How many zeros are here total? 6. So that means that this is really 1,000,000 cubic centimeters. Right? 1 cubic meter is 1,000,000 cubic centimeters. Right? That is the conversion factor for this problem. So I'm gonna, for the sake of space, I'm gonna erase this. Okay. You could either have it oriented with meters on top, and cubic centimeters on the bottom, or vice versa. Or in theory, if you're familiar with scientific notation, you can simply write this as 10 to the 6th. Anyhow, what is suspicious, or what you have to be careful of here, rather, is this. This is not 1 to 1, it's 10 to whatever it is. Right? So, if you have the conversion factor, then you can get through this pretty quickly. You might just reason it through on your own, but here's the mathematical proof of it. Remember that formula, we'll use this a lot. What is given to you times the conversion factor, written in the style of a fraction, will spit out what you want as long as you rig it to do that. This is fading a bit. So what do we have? 10 cubic meters is what is given. Okay. And our conversion factor is this. 1 meter cubed is 1,000,000 cubic centimeters, which if we want to end up with this cubic centimeters, we have to put that above the line. Right, and 10 to the 6th would be more practical to write it as a power of 10, but we didn't technically go into that this semester, so I'm going to just write it out brute force here. 1,000,000, all right, to 1. Because this is strategically rigged as such, the unit here is diagonal to the unit here, so they cancel out of existence. And then it really is just 10 times this, which is just going to add a 0 to it. Which means that your answer is really going to be 10 to the 7th, which is 10,000,000. 1, 2, 3, 4, 5, 6, 7 cubic centimeters. That is the answer. Page. Hurt myself drinking. Need more water. Forgive me. Who's he out there today? The next problem has a diagram. Alright. Okay. Find the area of the blue shaded region, which is meant to simulate a sidewalk that is outlining somebody's house. So imagine this is their property, and this is a walkway around it. And it's a uniform walkway, which means that if it's 1.4 meters wide this way, it would be the same here and here respectively. Anyhow, you need this diagram to really answer this question. If you're going to find the area of just the blue shaded region, start by writing a even if it's very verbal, right, at first, that's fine. The area of the blue shaded region, aka the walkway around the house, would be equal to what? It should be equal to a total area that is basically the area of the widest perimeter minus the area of the house. Okay, now one thing that you do have to bear in mind, if I just spelled this correctly, is what is the shape that we're using consistently throughout this problem. They are, although this looks more like a sort of the side view of a transformer, I would say. This is a rectangle, the blue one. And this reddish orange thing here is also a rectangle. Right. So we're just going to use the area formula for a rectangle, which I'll put up here. Area is equal to length times width of a rectangle. Right. I'll draw the picture here. Let's see. This is not to scale, of course, but it's the general idea. This is the house, and this is a walkway that goes all the way around it. Okay. Anyhow, the dimensions given from here to here are 1.4 meters. The dimension given from here all the way to the other side of this red rectangle is 23 meters. And then because it's a uniform walkway, the same width all the way around, this is also 1.4. So if you wanted to get the total area, that is the widest and longest lengths and widths, all right, basically from here all the way around, which would seem to be the square one, but pardon me, the blue region, but it's not entire, well, it's incorporating both of those things. It would be what 1.4 plus 1.4 plus 23 would be, which would be 25.8 meters in total width. A similar situation arises when you're trying to consider the dimension all the way through this rectangle from here to here. If I could just draw this without any problems. There you go. It is a consistent walkway, right? So this is 1.4. In the picture, though it's on the opposite side, this is given as 8 meters. A house is generally narrower this way. Not really. Somehow, I've never seen a square house, but it is feasible, right? And then it's 1.4 this way as well. So this dimension would be 1.4 plus 1.4 plus 8. In which case you would get what? 10.8? It is these dimensions which a person would derive independently of the problem, the word problem, that you need to calculate the total area to start with, right? And it's just two things multiplied, 10.8 and 25.8. So you could start with that if you'd like. 10.8 times 25.8 is 278.64. And it's an area, so it's meters times meters, so it's meters squared. Okay. The area of the house is much more straightforward, right? It's just 8 times 23. This dimension and this dimension, which was given to start with. Right? What's 23 times 8? 184. So you're going to subtract 184 from the total area. Alright, 278.64 minus 184, and you would get 94.64. And that would answer the question, because this is what you're actually after. 94.64 meters squared. If I shaded it in, what we've calculated is basically this ring. It is a square sort of ring. And the reason I say that it looks like a transformer is every schematic I've ever seen of a transformer is a block of metal basically with a hollow center. It's square like that. And 94.64 is what you should get. So if they ask you to round, and I stole this from one of your questions online, it would be about 95. For problem 6 and 7, you would need a formula, which I wrote on the paper. There's two formulas actually. I have to hit this with the alcohol in a minute. Blue is being more tenacious today. Perhaps I have to opt for a different marker. Okay, now if you look at this test again, in the first problem it says convert 89 degrees Fahrenheit to so many degrees Celsius. This would be the appropriate formula where it is solved for C. Right? The next question is convert 20 degrees Celsius to so many degrees Fahrenheit. This would be the appropriate formula, which is solved for F. All right, so I gave them to you, you don't have to go looking for them. Notice a couple of differences here, aside from what is the letter on the outside. They involve the same ratio, well, flipped, 9/5, 5/9. But in the case of the Celsius formula, you really must do the subtraction first. Whereas in the Fahrenheit formula, you do this multiplication first. Okay, so just be careful of that. And this is what you have to convert 89 degrees Fahrenheit to so many degrees Celsius, and this is our formula. 5/9 times Fahrenheit minus 32. You can just superimpose the information into the formula. So 89 would go here. Because of the order of operations, there's a parentheses here on purpose. You really must do the subtraction first. Which means that this is then 57 times 5, and technically 9 times 1 if you write it in the style of a fraction. Right? There is no cross simplification that you can do. You just brute force have to multiply the top times the top and the bottom times the bottom. And if you want to, you could enter it in this arrangement in your calculator. That first, hit the division symbol, and the 9 last, right? In which case you get this. This ends up being 285 over 9, if you want to do it piecemeal. And this is 31.6 repeating degrees Celsius. If you had to round it, depending upon the place value, I forget, again, I stole this, but maybe 32 Celsius, which is not to be confused with 32 Fahrenheit. Okay. 7. I made this one up. If you were to convert 20 degrees, that's terrible. It's dying. Okay. Almost done. Okay. 20 degrees Celsius is equal to what Fahrenheit? You would need this incarnation of the formula. You could get one from the other by rearranging it. They're inverses, actually. F is equal to 9 over 5 C plus 32. Notice that the order of operations is different, though. You would have to do the multiplication here first. So, just to get this out of the way. Plug in the value given, 20, which makes this really 9 over 5 times 20 over 1. You could just simply do top times top and bottom times bottom, but it might be more strategic if you're doing this somewhat by hand. To cross simplify, you might recognize that 5 and 20 are made of the same factor, 5. So that means that this simplifies as 1 and this becomes 4. Alright, and therefore it is just 9 times 4, which is something you would add to 32. 36 plus 32 is 68 degrees Fahrenheit. Right. That is approximately room temperature, right? 20 degrees Celsius is 68 degrees Fahrenheit. Alright, for the next one, given a volume of water is 2,304 meters cubed, like a pool, I suppose. Use the reference table below to convert this mass of water into, this volume into a mass, which sounds weird, right? Because physically they're different measurements, right? We think of mass as being how much, matter something is made out of, and volume is the amount of space it takes up. Because of the nature of the metric system, right, it is simplified. There are these relationships that we could use as conversion factors, basically. Even though they're talking about different physical quantities, we can convert between different physical quantities at will. All right, that's why the table is there. All right. Most importantly, and I would memorize this, all right, 1 cubic centimeter is equal to 1 milliliter, right? And that is equal to 1 gram. 1 is to 1 is to 1, right? Use 2 in tandem when you're making conversion factors. If you know even just this much, you could derive anything that follows. I kind of went overboard on purpose. I wanted to really emphasize the relationship. If 1 is to 1 is to 1, then 10 is to 10 is to 10, and 100 is to 100 is to 100, and 1,000 is to 1,000 is to 1,000. The only other thing that you would need is this. A metric ton, which is abbreviated by lowercase t, is 1,000 kilograms, as opposed to an imperial ton, which is what in the United States we're more familiar with, is 2,000 pounds. We're not worried about that. Anyhow, what I wanted to encourage you to do is write one of these conversion models. I don't know why I'm always having such a difficult time breathing in this hallway. And the window is open. it's not asbestos. I'm answering questions as best as I can. Anyhow, in this problem, we may have to have several conversion factors in sequence. But, all right, this is the basic idea. We could rig a conversion factor, which is a glorified fraction, so that it cancels units and it brings us closer and closer and closer to what we want ultimately. So let's start with what is given. In this problem, 2,304 cubic meters is given. Okay. So, what could we convert to? Well, if our conversion factor involves a cubic centimeter, and we're trying to convert to this is a mass versus a volume here, we could at least convert to cubic centimeters first from cubic meters. And we actually did this before, right? Remember this? We technically had established that if it's 1 meter by 1 meter by 1 meter, and there's 100 in there, 100 in there, 100 in there, centimeters, then instead of 1 times 1 times 1, it's 100 times 100 times 100. Which means that in 1 cubic meter, there's 1,000,000 cubic centimeters. That was that earlier problem. That will get us to cubic centimeters, all right? We would then be able to convert, maybe I should put this in a different color. We would then be able to convert cubic centimeters into grams. All right? So grams is what we want to end up with temporarily, and cubic centimeters is what we would want to cancel out. It's a relationship of 1 is to 1. So 1 is to 1. Right? That might seem silly and unnecessary, but we do have to convert these units, so I would never apologize for that. And then lastly, we would have to change, almost lastly, we would upgrade grams to kilograms. If you're familiar with the metric system conversion between metric units of the same physical type, that is the same type of measurement, just lengths, right, or just widths, or just volume, whatever. In this case, it's masses. All right. In 1 kilogram, we know that there are 1,000 grams. This is information I took for granted a person would be familiar with at this point. The last thing would be to incorporate this conversion factor here. 1,000 kilograms is 1 metric ton, which is what the question is asking. Convert to mass, right, from what apparently is a volume in metric tons. So we need this extra tidbit of information. So I'm going to hang on here and squeak this in here. I ran out of different colors. 1,000 kilograms is 1 metric ton, which is abbreviated by an italicized T. Okay? This machine is good to go, right? You could brute force your way all the way through it. 1 times 1 times 1 times 1,000 times 1,000. That's all the bottoms. And brute force the tops. 2,304 times 1,000,000 times 1 times 1 times 1. But really what we were after is the unit conversion, and we're going to verify that this is going to produce what we want now. Everything that is diagonal is the same. We can cancel. Cubic meters is canceled by cubic meters. Cubic centimeters is canceled by cubic centimeters. Grams is canceled by grams. Kilograms is canceled by kilograms, and what we're left with is the unit in question. Metric tons. A similar effect could occur with these thousands that are here. All right? When it comes to powers of 10, or basically anything that has a lot of zeros in it, you could pull a mental math skill, right, if you feel comfortable. As long as one is below the line and another is above the line, it doesn't matter if they're separated very far apart. As long as it's multiplication, as it is, all right, you can get away with crossing out zeros. It's more or less like this. If you had 1 million sitting above 1,000, it has the identical relationship to 1,000 to 1. So if you cross out pairs of zeros above and below, you can simplify the calculation without even a calculator. So 3 zeros here crosses out 3 zeros here. And coincidentally, another 1,000. So the same effect, all right? These 3 zeros would cancel out these 3 zeros. And again, you can verify this with your calculator, brute force, top times top times top, and bottom times bottom times bottom, and then settle it after the fact. But look what you're left with. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Everything is 1. So 2304 times 1 is unchanged, is unchanged, is unchanged, is unchanged. And the denominators are now 1 and 1 and 1 and 1 and 1. So that means that actually 2304 cubic meters is 2304 metric tons. And we're not knowing unless we rig the machine to do that. Welcome to the machine. Okay. Anyone like Pink Floyd? Well, you should. Okay. Anyhow. Moving on. Here's number 9. I definitely stole this from your online assignments. I felt this was kind of an unfair question, especially the way that it was drawn. So I drew this myself, and I tried to explain the background information that the author seems to be assuming that anybody knows. If you really wanted to do this particular problem comfortably, I would argue that you would need to recognize it from a physics class. All right. Anyhow, this is my reincarnation of that problem, right? With the aim of trying to make it more obvious what is going on here. I'm going to have to draw this, unfortunately, so bear with me. They're asking you to find a mass based upon conditions that are illustrated by the diagram. I'll fill in this with a erase. So they drew this basic teeter-totter looking thing, a seesaw, which is kind of like a scale, if you will. The scale is meant to balance, right? And you see a long end of this uneven seesaw this way, and a shorter end of it this way. And there's a box sitting here, and then a second one sitting here. And they tell you that this mass is 5 kilograms. And we want to know how many grams this is. There's a lot going on in this problem. Unit conversion, and also trying to figure out how these things would balance, right? Now they also tell you that the length of this lever here, without using the word lever, is 2 meters, and this is twice as much. This is, it's disguised though, it says 400 centimeters. Now, basically what this is a torque problem. And torque is, if you can think about it, a twisting force, essentially, a turning force. It has another name, it's sometimes referred to as moment. Right. But torque is probably more common, right? Anyhow, the key phrase, the operative term here is that it's a force, right? Which means that it is some derivative of this formula, which was not given to you in the problem, weirdly, right? A mass times an acceleration, ma. All right. Now, the kind of force that is being applied here is weight, right? Because there's no human actively pressing on this. It's just a block or whatever. And there's a weight here. This is a type of force, right? So, we have a torque here, which I'm going to just abbreviate T. It's usually tau is the physical symbol for this, tau. Right? And it's the first one. This is the first mass and this is the first length. And this second torque here is from these two things. All right. If this is balanced, and that is again the really key phrase I should say, the torque here, that is everything involved on this respective side of the seesaw, must equal ultimately the same quantity on the opposite side. Now the individual parts will be different perhaps, but the overall product or whatever is involved, all right, I don't want to give away the story yet, they have to be equivalent. The formula for torque I wrote here, all right? It is a force times the length, all right? The length of the lever, all right? It is a similar looking formula to work, right? But work is a distance that something moves, whereas the length of a lever is something that's not really moving in the traditional sense. It's just how long this is, right here and here. I'm going to write what this is underneath it. If this is a force times a length, that's the first force and the first length. And on this side, this is a force and a length. This is a second force and a second length. All right. This is again information that the author of the problem took for granted, perhaps that you know. The force is a mass times an acceleration. We definitely have a mass here. The acceleration, the weight incarnation of force, would be this. Mass times, instead of A in the horizontal, it would be A in the vertical, which is G, right? If you wanted to be technical, 9.8 meters per second squared, that's what G is, right? It turns out you're not going to need that because there's going to be a cancellation effect, but to expand upon this, here's where it gets to. You would have on one side here this weight force, because it's pressing down due to weight, so presumably, which would be M times G, this is M1, times L1, and on this side, M2 times G times L2. Now, a couple of things to bear in mind. You do indeed have different masses, right? We don't really know what that is, but we assume that it's going to be something different. So the mass here is 5 and the mass here is whatever it's going to be. We have different lengths. This is length 1 and this is length 2. That is apparently different. Yeah. One thing that is the same on both sides of this is what would have been the acceleration, which we're calling G in this case because it's a weight. If everything is being multiplied here and here, then we could actually remove G right out of the problem. If you wanted to rearrange the pieces by dividing by G, like this to move it around, this would be the effect. The G's would cancel out of existence because they're the same thing on both sides. They're not even different signs. They just go away. Which means that this teeter-totter situation, this balancing act, is really asking, well, whatever M1 and L1 is, what would M2 and L2 have to be? There is some conversion that has to occur here. I'm going to put this over here because it's getting sloppy. This is basically what we're going to use now. Let me, before I erase anything, start with this. We want consistency in the units. Technically, if we were talking about a force, this would have to be kilograms and that would be meters and that would be fine. But this would be kilograms as well. So, and this would be meters as well. Let us do one little tweak here. 400 centimeters is how many meters? Just to be consistent. 4, right? Meters. Right? If 1 meter is 100 centimeters, then 4 meters is 400 centimeters. It's times 4. Right? And you could convert it with the diagram if you like. Anyhow, if I filled in as much information as I could, this is what you would get. And I'm just being careful. Be consistent with the units. Okay. So in place of M1 and L1, I'm going to put 5 and 2 basically. 5 kilograms times 2 meters, and that would be 10 kilogram meters, which is technically, well, that's sufficient for right now. Okay. And I get into newtons or anything else, which would be meters per second squared, but forget that. It's 10 from 5 times 2. And these are the units that would be involved. On the opposite side, this is what we're looking for. So we don't really know. It looks like from Mario Brothers, right? And this is 4 meters here. What we can do, since the question is really asking us what would this have to be, is rearrange this algebraically to solve for that missing value. What is the opposite of multiplying by 4? To divide by 4. Here and here. Insofar as the units are concerned, the meters would then cancel. And then you'd have this relationship, that this mysterious quantity is 10 kilograms divided by 4, as the unit meter cancels. Right? If you divided 10 by 4, what would you get? You'd get 2.5, so 2.5 kilograms. Right? But the answer wants it also simultaneously, it wants it in grams. So you'd have to convert as an afterthought. 2.5 kilograms to so many grams. And that is a matter of just, if you draw a diagram or if you happen to know there's a difference of a factor of 1,000 here. Converting from kilograms to grams is to move the decimal point towards the right 3 spaces. So it will be 1, 2, 3, and you'd have this as an answer. 2,500 grams. There's a lot of background information, and perhaps even if you weren't aware, you could finagle it. And I thought it was kind of an unfair question without having the background information, so I try to at least draw the picture in a slightly more intuitive way and then give you the formulas. Hopefully. Hopefully that helped a bit. Okay. That was problem 9 from the sheet. the bottom of this page, there is again a table for reference, and you're going to convert these 3 problems. I'm going to sip of water. So for 10, you have this. Convert 2 gallons is equal to so many liters. This is a situation when you're converting from an imperial unit to a metric unit. So it is conceivable, it's just not going to be as clean a finish. Because you're converting from one system to another, there may be some slight loss in translation. They don't perfectly align, but we do have conversion factors, and they're listed in this table here. Right? They're always sort of written horizontally, whereas when you're trying to implement them, you might put them more vertically. Yeah, that is to say, in the style of a ratio. So in this first situation, if 2 gallons is what you're given, and you want to convert this to liters, then you need liters above the line and you need gallons below the line. And it just so happens that the relationship is that in 1 gallon there are 3.8 liters. Be suspicious. If there's a decimal, that probably means that something was rounded, which means that, again, it's never going to be perfect, realistically, going from one type of system to another. But within a system of metric units, it is perfect because it's just powers of 10. That's another reason why the metric system is better. All right, because you're not going to lose there's not going to be a loss in translation. Even in the imperial system, if you're just stuck with that exclusively, you may get in trouble. All right? Anyhow, gallons cancels gallons, and it's 2 times 3.8, which is what? 7.6 liters. This is really fading. You'll brew soon. Okay. Number 11. You have 5 kilograms, and you need to convert that to pounds, lb, which is Latin. Libra pondo, 1 pound weight. Okay, again, start with what is given, 5 kg. The conversion factor that is available, at least on the table, is that, well, let me figure this. If pounds is what you want, that has to be above the line. If kilograms is what you're looking to cancel, that has to be below the line. In 1 pound, there's 0.45 kilograms. Right? There is another thing, not to digress here, but if you had it from the perspective of a whole kilogram, 1 whole kilogram is approximately 2.2 pounds. Right? Just for reference. Anyhow, kilograms cancels kilograms. In this instance, because of the way that it works out, this is all 1 technically, you're going to divide 5 by 0.45. And you get this. To be ultra precise, it would be 11.1 repeating. And realistically, you would probably round it, so about 11 pounds. Something like that. They have to specify that. The last of this type. Uh, 80 meters, pardon me, 80 miles, which is abbreviated MI, converted to so many kilometers. If you have 80 miles, MI, not meters, the conversion factor would have to be rigged like this. What you want above the line, what you're trying to cancel below the line. And according to the table, you can see it again here. 1 mile is approximated as 1.6 kilometers. So 1 would be down here, 1.6 would be up here. It's purely a multiplication problem in this case because it just has 1 as a denominator. So this times this, you would end up with what? 128 even kilometers. Okay. Alright, now we're shifting into chapter 8 material, which is geometry. I'm going to spray this board here because it's getting really messy. Alright. Now, for problem 13, here's this diagram. Right, to answer this question, I wrote it what the question is verbally here and then more symbolically here. This means the same thing as what you see in blue. But I need, unfortunately, to duplicate this to discuss it. So humor me for a moment. Right, you have a horizontal line. This is dry. This is problem 13. You have a line running this way, and then another one running this way, and another one running this way. And there are points that are indicated as these 2 points, A and B. And over here you see C and D. And running this way you have points E and B again. And F and G, and lastly you have points H, C, and I. And the question that is actually the question for 13 is this abbreviated. Now, using the diagram, what is the intersection? That is the symbol for intersection in a sort of a horseshoe shape, upside down U, because U is reserved for unions, right? Of ray FB and ray EB. What are you left with? Remember, if you are talking about an intersection, then what you want is an overlap. All right. When it comes to rays, this is the starting point, the first letter. And this is the starting point here for this ray. So I'm going to try to sort of highlight it, right, to illustrate. Let us sort of draw a highlight on top of the ray that is FB. And incidentally, ray is indicated by an arrow above these 2 letters. Right? This is F, starting point, and B happens to be an extra point on the line. Doesn't mean it stops there. It just is meeting the minimum qualification to be a ray. You need 2 points, and then a ray by definition stretches into infinity, even past that point. Right? But this is where you start, and this is where you're headed. Okay. Simultaneously, there's a second ray here, which is, I'm going to put it green here, which starts on E, which is there, uses B, the same point coincidentally, just to define it, it needs, again, 2 points. And if that's the starting point, and this is where another point on its line, it's running in the opposite direction, beyond even the letter B. So the real question now is, if we're looking for an intersection, where are these opposite lines overlapping only? Well, they're overlapping strictly, right, from here to here. including those endpoints, but just in this space, if you will. This segment is really the word I should use. So what is the answer, although I obscured it? It is the line segment, which we abbreviate by, oh, it's the end of that marker. Both of my blues gave up on me today. It is the line segment that runs, and the line segment is abbreviated by just the line above two letters, BF. You may have seen other similar looking incarnations of this, right, where there's a hole here and a hole here. That is a situation in which they're trying to specify that you don't include the endpoints. But since they do in fact overlap in those endpoints, you're just using a regular line segment. So segment BF, endpoints included, is the intersection of these two rays. Switch out to black. Okay. There's an observation. When my blue markers die, they stick to the board more, which to me implies that either the chemical is hardening or it's not evenly and thoroughly mixed inside the shaft of the marker. And I'm getting whatever is at the bottom of it finally that is making it stick more. Here is 14. Hopefully this will give me a couple more draws here. All right. You have the parallel line problem. I probably should have said that. All right. In retrospect, it would not be fair, all right, to not indicate that. These are supposed to be two parallel lines cut by a transversal. I really should have spelled that out. I took it for granted that you might recognize it at this point, that this is the situation. One should never assume, and when you're a teacher, if nothing else, cover your rear end. Write out what the picture is describing. So, you know, like, I could draw a picture of Abe Lincoln, right, you know? And go, look, it's Abe Lincoln, but it doesn't look like him, right? So if I write Abe Lincoln, you know, above the very poorly drawn, you know, copy of Lincoln, right? Then people, he looks like he's sticking his tongue out and might have beard, all right? Then, you know, this would save me, all right? No parents could get mad at you when you have spelled out Abe Lincoln, even if this is badly drawn. In math world, you know, same thing, okay? This looks like two parallel lines, but you need to write that. I should have. All right, anyhow, it's labeled like this. That the measure of angle 2, and this is angle 1, 3 and 4, all right, and this is 5 and 6 and a 7, and there's the measure of angle 8 here. The measure of angle 2 is 26 degrees, but the measure of angle 8 is unknown. Right, now there's probably several different ways that a person could figure out what this is. All right. We have, just to list some relationships that are good to know. Vertical angles exist here. We have corresponding angles. Alternate interior angles and alternate exterior paint, sounds like, angles. These are four, and well, technically, another one, supplementary angles. I would at minimum know these five, alright? You don't need to know anything else but what this is, and the fact that these are in fact two parallel lines cut by a transversal, right? Because that means that there is some symmetry here. Right. If angles are supplementary, there is sum there of two that equals 180 degrees, right? Vertical angles are congruent. Right, that's the symbol for congruence, which essentially means equal. Corresponding angles are congruent. They're different arrangement though. Alternate interior are congruent, and alternate exterior are congruent. They're just in different places. Right? Just as an example, I'll give you this much information. Angle 1 and angle 3 are an example of vertical angles. Right? They're across from each other. They're across. Okay. Corresponding angles are something like angle 2 and angle 5. Right. They're on, there's one inside, one outside, parallels, and they're on the same side of the transversal. All right, that is the definition of corresponding. This corresponds to this. That's not the only pair, but you know, like 1 and 6 as well. But notice that they're both, 1 is inside the parallel lines, 5 is inside the parallel lines, 1 is outside the parallel lines, that's 2. But they're on the same side of the transversal. Right. Alternate interior, right, are opposite sides of the transversal, but both inside the parallel lines. So something like angle 4 and angle 5. They're inside the parallel lines, alternate in respect of the transversal line. One is here, one is there. Right. Alternate exterior is something like angle 2 and angle 7, which is what I ended up using myself when I tried to answer this question. All right. They are outside the parallel lines, right, on opposite sides of the transversal. Hopefully that is in the frame, and if it's not, I'll adjust the camera. Sorry, it's a bit faint, right? My board is getting messier and messier. Okay. That, again, there's probably several ways to go about this problem, but that is ultimately what I went with. All right. Angle 2, this angle here, is alternate exterior. They are exterior in that they are both outside of the parallels, right? And they're alternate because they're opposite sides of this transversal line. So, angle 2 and angle 7 being alternate exterior angles are congruent. They equal. This is technically the congruency symbol. So if this is 26, then this is also 26 degrees, right? Then to answer the question of, well, what is angle 8? The angle 7 and angle 8 are supplementary, right? Which means that their sum would be equal to 180. This is a straight line, and straight lines are 180 degrees. So if even this is mysterious, as long as we have one or the other, and now we know that this is 26, we could infer what angle 8 would be. Right? How so? From subtracting from 180. It should be 154 degrees. Sorry for the messiness. 154. That is angle 8. Moving on. Alright, let me get a sip of water again. Next. If you look at problem 15 on the next page here, using the formula for the sum of the measures of the interior angles of an n-sided polygon, remember polygon is a two-dimensional shape, right? That is not a circle technically. Determine the total number of degrees for that of a triangle, right? So kind of the total number of degrees of a triangle is kind of a fun fact that a person should know. But if you didn't, and you somehow knew this formula instead, you could calculate that. Right? A triangle has how many sides by definition? Any type of triangle. 1, 2, 3. So if you inserted 3 in place of n, 3 minus 2 is 1. 1 times 180 is 180 degrees. Okay. When you do problem 16, it would be useful to have this formula handy. You're not going to use it exactly in the same way, but you will use it part of the way. Here's 16. Given what is true about regular polygons, that they are equilateral, that means that all of the sides are equal, and equiangular, which means all of the interior angles specifically are equal to each other, what must the exterior angle be in the drawing below? Is what appears to be a hexagon, right? This is 6-sided. If you have a hexagon, and it's a regular hexagon, that means that any of these angles here would have to be identical. Right. Let us figure out what one individually has to be first, right, before we get that exterior angle. We would go back to this formula. You could use this for something that is not regular, but you need it to be, to take the fact that it is a regular hexagon into consideration. All right, how many sides does it have? 1, 2, 3, 4, 5, 6 if it's a hexagon, right? So you have the 6 for number of sides. 6 minus 2 is 4. 4 times 180 is what? 32, carry 3. 720 degrees total. All right. Now, this tells you what it is total. What is any one of them individually? They're all 1, 2, 3, 4, 5, 6 interior angles. So you would have to divide this by 6. If you divided 720 by 6, you get the individual angles. 6 goes into 7 once with 1 left over, into 12 twice, into 0. That means that right here, this is 120 degrees. All of the other ones are 120 degrees as well because it's regular, right? But based upon that information, you can figure out what the question mark is, the exterior angle, right? How come? They're supplementary again. If things are supplementary, they add up to 180. So it's going to be 120 plus this question mark, whatever it is equal to 180 degrees. And it technically is an algebra problem, or you could just figure it out. All right, minus 120, minus 120, 180 minus 120 is 60. This angle in here is 60 degrees. Now this took up 2 pages just because I felt I should explain. Yeah. I wrote this just for information that I thought was useful. Right. Whereas congruent figures are completely equivalent in terms of their angles and side lengths, similar figures are proportionate, meaning that they have corresponding side lengths which, although not equal, are either larger or smaller by some consistent factor. Taking this into consideration, use shadow reckoning to write a proportion equation and indirectly determine the height of the tree in the diagram below. This is the instruction for problem 17. This is the diagram on the next page, which after having stayed up late and writing this, I just started to get a little wacky. Okay, anyhow, I think this is cute. Look at this happy sun here. All right. This is a situation where you have similar triangles, right? If you humor me, here's a tree. Right. And it's going to be a very tall tree. And here's a person. Looking happy, living their best life. And here's the sun. Right, casting rays, right, but technically throwing shade, right, so that you have basically similar looking triangles, one sort of superimposed upon the other. I modified this problem a little bit from where I've taken it from, just because I didn't want to get too complicated. There, the shadow length, that is the total shadow length from here to here, is 120, and the unit in this case was feet. Right. The shadow length that was from here to the same point that is the shadow cast by the person, is 8 feet. Right, now simultaneously, perhaps I should do this in the same colors here to make this easier to read. The height of this person is apparently 5 feet, and what we're actually after is the height of this tree. Right? This is called shadow reckoning. and it is an indirect measurement. Now, why have this sort of a thing? It is easy for a human, a terrestrial organism, to measure along the ground, right? Because no matter how tall you are, you could easily measure along the ground, right? No one is 0 inches tall, all right? It is more of a challenge for us, vertically challenged people, to measure the height of something much taller than us, right? Even if you had a very tall ruler, you know, you'd get into some trouble really quickly. Anyhow, shadow reckoning is an example of the use of a proportion equation. Yeah. Why did I take that? It's an example of the use of a proportion equation, right, which is basically a fraction set equal to a fraction, meaning that there's 4 voids that you have to fill in. Okay. Similar figures, they're not the same size, right? Similar figures, but they are proportionate. So if they're proportionate, you could write a proportion equation to figure out indirectly what the height of this tree is. Right? Just be, as is the golden rule of math, be consistent in how you arrange parts. There may be more than one way to do this, not the way that I choose, all right? But be consistent, all right? My logic is this: reserve one fraction for the tree dimension, and then reserve the other fraction for the person's dimensions. Okay? And even further still, be consistent. Let us say that the top of the fractions in both cases are the height, or the 2 heights, right? And the denominators are the shadows. Here, one triangle, that's this one, here is superimposed upon the larger one, but I've already taken that issue out of the problem, the way that I've illustrated it, okay? The total from here to here is 120. Where I stole it from, they gave you the dimension from here to where the person is standing, and then you had to infer that you needed to add the extra part, but you don't have to worry about that in this case. Anyhow, let us say this is H, okay? H is actually what we're looking for, right? The shadow length cast by the tree is 120. You could leave out as long as the units are the same, they're all feet, then you don't really need to worry about them. If one was in inches, or, you know, heaven forbid they were in some other unit system, you'd have to convert everything to the same type of unit first, right? That's not an issue here. Height is the top, so 5 would be corresponding, all right? These heights are corresponding. They're not the same, but they relate one to the other. And similarly, the shadows are corresponding. They're not the same, but they relate to one another. They're the same type of measurement. Anyhow, 8 is the dimension that would be here. And now that you have that rigged up, I need a little bit of space here, so I'm going to work over here. You solve proportions by cross multiplying, which is basically to multiply diagonally this way and multiply diagonally this way. This is fading out too. So, what is the abbreviation for 8 times h? The good etiquette of math would have us put the number in front, the coefficient. That is one side. What is the outcome of 120 times 5? That is the opposite side. And And then in order to solve for h, we have to move 8 from one side to the other. So you would divide by 8 here, and divide by 8 here. You may wonder, well, why didn't you just do the multiplication first? Just a good habit. If you are using your calculator, which I would never fault you for, arrange all of the parts to where they need to be before you employ your calculator, because you can't use a calculator anyhow until you have basically all the numbers involved. So you could now at this point type 120 times 5 and then hit the division symbol immediately after and then divide by 8. I've learned to do this because sometimes if we're doing something that involves like an irrational number like the square root of 2 or pi, all right, you end up having to round in the middle of the calculation, which is a big no-no. All right, you get a bad answer, a less accurate one anyhow. This round off, right? Anyhow, this should work out nicely. It actually, just dumb luck. This is going to be, it terminates this this fraction here. So you end up with this 600. And if you did a piecemeal, and you end up with 75 feet, which to me is kind of suspicious. It is possible for a tree to be even taller than that. But that's just that's a very, very tall tree. I think even the trees that are outside my window here are maybe no more than like 25 or 30 feet, right? So this is like a redwood tree. I should have made this red instead of that. 75 feet according to the dimensions that are quoted to us. Coming into the home stretch here. All right, if you look at 18, 18 is use the Pythagorean Theorem, a squared plus b squared plus, a squared plus b squared equals c squared, famously, to determine the area and the perimeter of this triangle, right? Why do we need that? Because one of the dimensions is missing, and it's one of the more integral dimensions. If the hypotenuse technically was missing, you can get away with it. I'm gonna not use blue for the rest of the day because it's dying and it's weirdly sticking as a result. Lingering. Bad seed to go in the cup there. Okay. For problem 18, this is the picture that you have to work with. You have, for sure, a right triangle because I took the time to put that box in the corner. So even non-verbally, that signifies that this must be a 90-degree angle. Right? And the dimensions are C is equal to 25 inches this way. And A is equal to 20 inches this way, and this B here is unknown. Okay. Now, if you calculate the area and then the perimeter, remember the difference between these two. An area is a measure of the inside surface would be technical, and perimeter is a measure of the outside around, and its most concise definition. The formulas for a triangle specifically are these and these, or this and this I should say. I'm going to abbreviate it tri. It's the base times the height over 2. Sometimes they put a half out in front. It equates the same way. A formula for area, perimeter, would be using the letters that happen to be here, A, B, and C. would be A plus B plus C. You could label them anything you want, and this is probably less common that you would be asked a question like this, but that is correct. It is the sum of all of these things, the sides. All right, now notice something. The B needs to be known in order to answer this question. What is the area? The B needs to be known in order to answer this question of perimeter. So how do we calculate that? The Pythagorean Theorem. Famously, a squared plus b squared equals c squared. It needs to be rearranged, and we do need to understand what the individual parts are. All right? But it's feasible. This is definitely a doable problem. All right? Let me explain one thing. I will reluctantly use my blue marker now. A is a leg, is what it would be referred to as. B is also a leg. The things that are basically beside these two intersecting legs, the things that this box of 90 degrees is formed by is a leg and is a leg. What is across from it is the hypotenuse. The legs are interchangeable, but the hypotenuse is non-negotiable, right? This is the longest, no matter what. Now all of a sudden it's behaving better. Maybe because it is upside down. Okay. So that means that you could use 20 in place of A, and you would use 25 in place of C. It would have to be that in place of C. Right? You could basically figure out what 20 squared is and what 25 squared is first, if you like. Or you could purposely rearrange this using A, B, and C only to solve it for B specifically, right? Whichever you prefer. It might be a little bit more intuitive if you just have one letter, so I'll do it that way. 20 squared is really 400. 25 squared is really 625. That is 20 times 20 and 25 times 25. We need to rearrange this to get B isolated. That means I'm going to move 400 from here over to where its friend is. Okay. What is the opposite of adding 400? Subtracting 400. These would cancel. B squared would be left over. And then 600 minus 400 is what? 225? Okay. The last thing is that this is nearly complete, but we just want B. We don't want B squared. So now we need to perform another opposite operation for the sake of algebraic process here. What is the opposite of squaring something? Square root. And if I square root this side of equals, I am obligated to do the opposite side. This cancels this essentially, and that tells you what B is. The square root of 225 is 15. Therefore, B is 15. Which means now I can insert 15 here and 15 here. And the other dimensions, in this case H, A is representing the height in this case. So this is also the height, because a right triangle is, it doesn't have that dashed line on the inside. Normally it looks like that. If you have a right triangle, it's just a leg. All right. So this is 20 in here, and that's 20 in here, and then C is 25. Okay. You could do some simplification before the multiplication, or you could do a brute force, whichever way works. All right. I like to do the simplifying up front if I can get away with it. All right. Because these are factors, that is, these two things are being multiplied, there's just this one denominator here, you could simplify the 2 and the 20 immediately. Their relationship is this. That means that it's really 150 times 10, which means it's 150. Pardon me, it's 15 times 10, which means it's 150. If the unit the units involved are inches, then it's inches times inches, which is inches squared, which is what areas have to be. Right? In this case, it is just adding inches to inches to inches, which means the answer is going to be inches degree 1. But what is 15 plus 25 plus 20 in whatever arrangement you want? There's a commutative property. You could move the parts around if you like. All right. 40 plus 20 is 60. And that's the perimeter. Okay. Yep, the black is starting to die too. The circle problem is similar in that it is asking for an area and a perimeter. This is problem 19. Given this drawing, find the area and the circumference. Remember, circumference is the preferred phrase when we're talking about the distance around the circle. So if you have this, wow, that is really faint. Try that again. No, that's still lousy. I think that's done too. Try this one, maybe it'd be half done. That's a little bit better. This is never mind. The dimension, I drew this to be very precise. All right. This is kind of overkill. If you notice that it has cross lines here, all right, that's just because I wanted to find the center, all right. Okay. Anyhow, minimally what you need is to know that this is in fact the center, and that this dimension from the center to the edge would be a radius, all right. If it happens to be 10 centimeters, then so be it. All right. Now, if you were going to calculate the area once again, and the circumference in this case, just in lieu of the word perimeter, we understand that an area is a measure of the inside surface to be technical, and circumference is the outside, for lack of a better phrase, around. Okay. The formula for area of a circle specifically is this. I'm using subscripts. Pi times the radius squared. Remember, it has to be squared if we're going to have an area. The circumference is usually given to you like this. It's pi times the diameter. Okay. The diameter would just simply be twice as long. Right? So you could finagle it one way or another if you need to. What I would do, since we're having to incorporate pi in a famous irrational number, is hold off until just before you use your calculator to substitute any particular value for this. Like a lot of times people use 3.14 or something slightly more precise, 3.14159. Right? Slightly more accurate, I should say. Or even 22/7, which is an approximate. Right? In calculus, what they do is they don't bother to use an actual number here, they just leave the symbol, because it's technically a perfect answer then. It's less satisfying to us maybe as humans, but anyhow, we're going to follow the order of operations, which means that before we multiply anything, we have to square. The radius is 10, so I would squeak a 10 in here. Centimeters. 10 squared is 100, which means that this is 100 times pi centimeters squared. Right? You can now use your calculator, right, and substitute for pi if you want to do it by hand. 3.14159, whatever it is, into infinity. Right? And take advantage of the fact that if you're multiplying by 100, the effect is that if you have two zeros here, you're simply going to scoot the decimal point over 2 spaces to the right, which means that your area is going to be 314.159, whatever it is, into infinity. If you round to the hundredths place, the hundredth place is what I think I specified on here. Yeah, round to the nearest hundredths. Hundredth. All right, that would be where the 5 is sitting. All right, so approximately 314.16. All right, centimeters squared is the area. Decimal point there. If you don't like this version of the circumference formula, there is also famously this alternative. The 2 out in front, that comes from this relationship. 2 R's is D. They just put the number in front because it's better etiquette. All right. If it makes more sense, then just rearrange the parts like this. 10 would go in here again. And then it is 2 times 10 rather than 10 squared, which means that it's 20 times pi, right? In calculus, that would be the preferred way to write it, believe it or not. Right? Just 20 and then the pi symbol. If you now substitute 3.14159, whatever it is, or use your the pi button on your calculator, here's what you would get. Right? Here. Remember, your calculator, if you have this type at least, it has a pi button. A scientific calculator usually does. Pi times 20. And you see 62.831 and so forth. The circumference is therefore 62.831, whatever it is, right? Rounded to the hundredths place would be where this 3 is sitting. So approximately 62.83 centimeters. Centimeters, degree 1 rather than degree 2, is appropriate for a perimeter, which is what a circumference is, essentially. All right. Nearing the end here. This is the end, my friend. Okay. This problem at the bottom here is just an example of using Euler's polyhedron formula. If you know all 3 of these parts, vertices, edges, and faces, they would add, no matter what type of polyhedron, would add up to 2. If you know 2 of them, you could arrange it algebraically to figure out the missing one, which is what this problem is actually asking for. How many faces would there have to be for a shape that has 13 vertices and 12 edges? Let's see. This is 20. V minus E plus F equals 2. Any polyhedron, a 3-dimensional shape, which would exclude spheres again because they don't actually have faces. They're enclosed, but they don't have faces. They're not flat. All right. Anyhow, if according to the problem we're dealing with 13 vertices and 15 edges, do combine what you can and then rearrange the parts to solve for F to answer the question of number of faces. This is going to give you a negative number. 13 minus 15 is negative 2 plus F equals 2. But when you rearrange it to solve for F, that is to get F alone, what ends up happening when you bring negative 2 over to the opposite side? You would have to add it, and the number of faces would be 4. So it all works out in the end. It all comes out in the wash. Right, next one, last page, is 21. I was thinking of making this an extra credit, but I'm giving you the credit anyway. Find the volume of this square-based pyramid. Okay, let me draw this really quickly. You have a square-based pyramid. It looks like a parallelogram because of perspective, but it's supposed to be a square. Square. Label it. Maybe I should make that a little bit shorter. Okay. And everything is going to come to a point. So, this back will come to a point. And this front would come to a point. If I could just draw straight, it would be great. This is why I failed at art school. And they wouldn't let me in school. Okay. Perhaps I should use a ruler, but forget it. Now, this is square-based, which is important because the formula for volume, this is problem 21, the volume of a pyramid PYR, AMID, I always forget that, is 1/3 capital B times H. All right, this is different from a regular B because this is the area of the base. Whatever the shape happens to be, there are other types of pyramids, right? You could have a triangular base, right? You can have a hexagonal base, and it gets more and more like a cone the more sides you have. Anyhow, we need to know that this is square. It is implied, non-verbally really, in the drawing because it says the dimensions are 8 centimeters here and 8 centimeters here, right? Now it could in theory be a rhombus, all right? But I also mentioned that it was square in the instructions, right? Anyhow, if we figure out this area, right, the formula for the area of a square, you can get away with using length times width. It is usually given to be more specifically side squared, right? They don't bother to use labels like length and width anymore because they're the same, right? So if it's 8 times 8, that's a cheat, right? This is 64, all right, centimeters squared because it's an area. And I have 1/3 here, and although I neglected to do it, in the drawing there is a dashed line that runs this way from the top down to the inside middle, and there's that symbol for a 90-degree angle there. I put the height up here, right? That is 12 centimeters. All right. So filling that in the formula, you have this 12 centimeters. Notice that this is going to be fine in terms of the units because it's going to be centimeters squared combined with centimeters, which is naturally centimeters cubed, right? As a volume should be. If you want, you could enter this into your calculator exactly as you see it. When there are fractions involved, I intuitively, and I want to encourage that, try to get them out of the way because they can cause problems. You know, you might have a repeating decimal. All right, so if you treat this as a fraction of 1/3 times a fraction times a fraction, you could cross simplify this and this becomes 1, so you don't even have to worry about the denominator anymore. This becomes 4. Right. So then it is just 64 times 4. All right. And 64 times 4 is what? 256. 256 cubic centimeters is the volume of a pyramid with this base at those dimensions. Cubed. Right. The second question is a surface area question. But this picture needs to be adjusted ever so slightly. I purposely duplicated it when I drew it, and then I made it in red because I wanted you to notice the one thing I didn't have in the original drawing. There's a blue line that runs this way, and then I made a little more obvious connector here between the center height from the point down out to the edge here. All right, look at this sort of interior right triangle that you see. All right, gotta read this. All right, find the total surface area of the same square-based pyramid. Hint, you would need to determine this, something called the slant height of the lateral faces. The lateral faces are these things that are running around coming to a point, right? In other words, not the bottom, all right? Try the Pythagorean Theorem, which you're already familiar with, and then round to the nearest hundredth place. All right, now, in the drawing, slant height is this blue line. Sorry, I'm using a blue marker here. And it is abbreviated S. It's a type of height, but it's not standing in the same place, it's just connected. All right, it's running along the face here, all right, as it would any of the others. If we're trying to get the surface area, all right, this total surface area, it would be this face and this face in the front and this face in the back and then this on the side and this other one in the back. There would be 4 triangles owing to the nature of this being a four-sided shape, plus the one square that we would have to calculate. We would need, since it's surface area, we would need to find the area of those respective shapes. Now, in the case of any one of the individual triangles, this is the formula for area of a triangle again. Base times height divided by 2. So we have 4 times this area plus, what did we calculate the square was? 8 times 8, 64, right? That would be the total surface area. That would be the 4 lateral faces, and the one bottom face. Okay. We need to find the area of these individual triangles, so reluctantly I'm going to use blue. In the drawing on the paper, there is this extra little triangle drawn here, which I'm going to highlight in blue. All right? I'm going to sort of draw it like this, shade it in. All right? There's a right triangle. Why is that important? Because although it's a 3-dimensional shape, what we're really after is this height of this triangle. This is called a slant height for obvious reasons, because it's slanted. All right. If you look at it from, that's this here, is the slant height, S. If you look at it instead of from the side, but sort of head on, all right, look at it this way. This is how it would look sort of head on. It goes from the same top, but it goes down to the middle of the base here, right? And this is a regular, ordinary lowercase b. Right? Lowercase b. This is head on. Right? Okay. Anyhow, how are we going to calculate S? Well, because it forms a right triangle on the inside here, and we do know at least 2 of the dimensions, right? We have to finagle a little bit. I'm going to erase some things that are not really important right now, like the line behind it. What is the dimension running from the center down? That's the actual height. It's 12. What is the dimension, not all the way across the bottom here, but this is to the center of the square. If it's truly a square, and it is, right, that means that this is halfway from here to here. If the whole thing is 8, what's halfway? From here to here, it's 4. We can now calculate this dimension, that is the slant height, for this purpose later, all right, from the Pythagorean Theorem. All right. We're just going to have to change the labels, right? If we call this B for base in this respect here, and this A, then this S is also C, all right? So if the formula Pythagorean Theorem is A squared plus B squared equals C squared, the labels as they were would have been the B here that I'm using is 4, all right? The A here is the H value, which is 12, all right? And the C value is the S value, which is what we're actually looking for, all right? Okay, so we have 12 squared is 144. We have 4 squared is 16. And that's 10, carry that is 160. We're gonna get a crummy number because it's gonna be irrational, but it's okay. S squared is equal to 160. Let's go the whole 9 yards and basically simplify this to just S rather than S squared. How do you get rid of something being squared? Opposite operations. You square root this, and then whatever you do to one side, do it to the other. These cancel. That means that S is equal to the square root of 160. Could you use your calculator to get the square root of 160? Sure, right? But it's going to be an irrational, infinitely stretching number. So leave it alone for right now. All right? Let us put it in here, right, where it is appropriate. This is the height now from the perspective of any one of the individual triangles. So I know that the labels keep changing and that is probably a cause for confusion, but don't be deterred, go slow. I'm just calling it height from this perspective of this particular triangle now, right? It's the square root of 160 that I'm tucking in here. The base is appropriately the whole thing. This base is now from here to here, right? And that is 8. I have all of these numbers involved. I have 8 times the square root of 160, yuck, right? And I have there's going to be times 4 ultimately because there's 4 triangles around this 3-dimensional object. And in the formula there's divide by 2, right? You can if you want to, because everything is factors, they're all being multiplied. You can simplify this if it makes sense. Or you could just, at this point you can get away with entering a lot into your calculator, including the square root of 160. But I try to do some of it by hand before I resort to a calculator. So let's reduce this 2 and maybe this 8 here, right? Or the 4, it doesn't work, it doesn't matter. This would be reduced to 1, and this would be half of that would be 4. That means realistically that this is 4 times 4, which is 16 times the square root of 160 plus 64, the squares area. Right? I would type this into a calculator because it's perfectly linear as you see here. 16 times the square root of 160, if you're going to use this in a certain order, I put a parentheses here, plus 64. Otherwise, enter it this way. (64) plus 16 times the square root of 160. This will, if you don't incorporate a parentheses, this will spare you a little bit of aggravation probably. So, it's the same thing, it's just putting the 64 in front. Okay, and this is what you get. Clear, sorry. I'm off by decimal place, forgive me 1 minute. (16 times the square root of 160 that is 16 times the square root of 160, which is 202 point something, plus 64. All right. So you get that, 266.385, right? Write it here. $266.385, whatever it is. That's because of the square root is 160. All right. If you rounded it to the hundredth place, which I should have specified probably, it would be approximately 266.39. And since it's an area, it is centimeters squared is how the units would work out. Okay. I just want to see something really quick. 64, yeah, if you, stupid calculators don't know everything that they should. There you go. Do be careful, right? I answered it the other way, 64 plus 16 times the square root of 160, because I think this would get you in less trouble if you typed that. But the first time I did it, it gave me the incorrect answer, and I can't help but sense that it's because of parentheses. So I want to just double check this. The only difference here, notice this, is asterisk that I put here, which is superfluous. I really didn't need to do that, but I did it, right? That's the way I had it initially, and it gave me the correct answer that you see here, 266. And this is the way that I'm entering. I tried it initially, and it gave me a dud. Come on. No, I went backward. No, it's not going to forgive me. Okay. Come on. Yeah, just do it again. 64 times plus 16 times 160. Here it is with the asterisk for multiplication, which it shouldn't matter, right? It's the rest of it, right? No, and now it's behaving okay. Maybe my calculator is getting the battery. Needs to be replaced. Anyhow, that is what you should get for the surface area. That is the total surface area, which is all of the lateral faces and the bottom. Okay? All right. I thought that was an interesting problem. Anyhow, like I said, this is going to be available to you in Canvas announcements. You don't need to, in Canvas announcements, you don't need to submit anything to me. I'm going to give you the credit for this. I just want you to work on your homework, really, especially if you're behind. Today's the deadline, so make sure that you do that. This is test number 2 to summarize. Okay? We are off on Wednesday because it is Veterans Day. All right, so maybe pay some respects if necessary. All right? I am going to the DMV because my car has to pass inspection. No, it may not be open. I have to go to Nissan because I have to have my airbag replaced. All right. Anyhow, too much information. Be careful out there.